This is the second presentation, of the day, and second to last presentation of TWSS 2022. With me is Dr. Daniel Main, who is one of our application engineers. Give you some background on Daniel is that he earned his PhD in computational plasma physics from CU Boulder in the area of kinetic modeling of the Earth's aurora, and he has worked as a research scientist at Los Alamos National Lab and the Air Force Research Lab. He's worked at TechX now for 3.5 years as an application engineer, specializing in a variety of areas, including low temperature plasmas, RF discharge, capacitively and inductively coupled plasma, and RF scattering via linear plasma dielectric models. Dr. Main wears multiple hats at TechX, including working on government-funded research projects, private consulting projects, helping customers backtrack their computational modeling effort, creating new examples, and helping customers with a variety of technical issues related to VSim. Yes, that is definitely true of what Daniel does for us. With his expertise in plasma, Daniel is kind of my go-to initially when we have clients that have particularly tricky problems. He's just amazing with it. So if you are working on a problem that is plasma focused, there is a chance that you will at some point talk to Daniel Main. All right, Dan, it looks like we can see your screen. And welcome. Everyone is super excited for this talk.
All righty. So today I'm going to be talking about this new example that we've been working on for a few months. We've spent even longer than that getting these capabilities exposed to users in a way that's easy to set up. Of course, easy is relative. So I will be adding on to the great presentation that Dan Murray just gave by going into some more specific example, in this case, this example, and showing you how to set this up in the visual setup. So just as way of a background, Dan talked about this a bit, and so I'm going to add on to what is VSim. So many of you listening in have been using Vorpal for, well, it's been around for 20 years, and some of you were in it from the beginning. And so at some point, we switched from using the term Vorpal to using VSim. And the reason is because VSim includes Vorpal along with the visualization setup, the post-processing capabilities, all within one package. VSim is a multi-physics, fully kinetic PIC code. So multi-physics means we do the plasma physics plus all the associated physics, or much of the associated physics involved with a plasma. So it could be reactions with neutrals, emissions from boundaries, all sorts of secondary processes that are needed to do the plasma part correctly. By fully kinetic, I think that's an important thing for everyone to understand what we mean by fully kinetic, because if you don't need a fully kinetic solution and you're looking for a problem that's going to run out on to second timescales, then something like VSim maybe is overkill. But if you need that detailed kinetic processes, if you need to know what's going on in the phase space of the electrons and the ions, then you'll need a code like VSim to solve that physics correctly. Electromagnetic means that we solve Maxwell's equations, the Ampere and Faraday's law to get the fully self-consistent electric and magnetic field. We do have the capability of doing electrostatic solves in the cases where the magnetic field doesn't play a huge role and the physics is dominated by the electric field. So let's move on to the advantages to using VSim for a magnetron sputtering problem. So VSim will compute the electric field self-consistently. So what that means is that we're going to solve, VSim is going to solve for VSim is going to solve for the role that the plasma plays in the electric field. And And so whereas a lot of codes will get you the electric field due to a boundary condition, this will also include the field due to the plasma itself, the plasma potential. And so when we start getting down into processes that happen near boundaries, this means that we're going to be solving for the sheath correctly. So that's extremely important when we get into the sputtering, the actual sputtering off of your cathode surface, because that depends on detailed kinetic processes. And so if you don't have the sheath physics right, then you won't have the acceleration of the ions onto the cathode correct, and you won't be modeling the sputtering correct. So VSim does all of that correct. That was a lot of negatives. So to put it into the positive, we get the sheath correct, and therefore we get the ion acceleration of the ions onto the cathode correct and model that sputtering process. In addition, we've recently added this external circuit model, which I'll be showing you in just a minute. We model just countless collisional processes, and we've added even more for VSim 12. We also can do secondary emission, electron emission off of the boundaries, and I'll show you how to add that in the visual setup. And then we based it on this paper here, at least the model I'm using. It's Furman and Pivy paper from 2002. And I already mentioned this already, but we are getting the sheath done correctly. Fundamentally, a sheath, for the most part, is a kinetic process. So if you're using a fluid code to model a sheath, which can be done, then you're by necessity including some sort of closure to get that correct, which is always going to be an approximation. So just as a brief overview of this extremely broad field, the goal of the magnetron sputtering is to create a thin uniform layer of some material. Could be usually metal, but it doesn't have to be. So we've modeled this as a copper cathode. This magnetron sputtering falls in the realm of chemical vapor deposition. And the advantages of magnetron sputtering over other techniques are we can work with over a pretty large pressure range of neutral gases. So in the literature, you know, I've seen everything from 1/10 to 5 pascals. It's a fairly small cathode voltage that can be used, and you can get pretty large deposition rates. So these are just some of the advantages of using magnetron sputtering. Okay, so so here's a picture of one sort of cartoon that I found. And so on the bottom, we're going to place our cathode, and underneath this cathode, there are going to sit a couple of permanent magnets, and then the anode will sit up here. In our simulation, actually, the anode is will be this right boundary also. And the external circuit connects the electrode and the anode, or sorry, the cathode and the anode separated by this resistance R. So we can get feedback from the plasma itself, which will modify and allow the cathode voltage to float. So here is a movie from my simulation. So let me explain the boundary conditions here. So this simulation is in a cylindrical geometry. So the R-axis is on the bottom, and then the Z-axis is this vertical axis. The white lines are the magnetic field lines, so the white vectors are the magnetic field vectors, and the color contour will be the potential. So the cathode actually goes from this left boundary over to about here. And then there's this transition region between the cathode and the anode. And then the anode is actually all of this here, the lower part, the upper part of this far axis, and then this right boundary, and then this top boundary. That's all the anode. So the initial voltage of the anode is grounded, and the initial voltage of the cathode was set to negative 470 volts. So it's a little, there we go. So it's a little hard to see the sheath forming. There wasn't a huge effect on the sheath. You do see the sheath getting thinner as the electron, the secondary, these are the black dots are the secondary electron macroparticles. And so it went by pretty fast. Not sure why that is, but there we go. You can see if I can go back here, you can see that the data was saved pretty coarsely every 3,000 time steps, and it ran for 120,000. So I have 40 data dumps, and within about 10 or 12,000 data dumps, you start seeing a noticeable population of secondary electrons. Okay. So the reason why this problem is quite challenging, and the reason that VSim can be essential for modeling this problem, is that if you were to try to do this analytically, then you would quickly realize that there are many parameters that need to be adjusted to get a steady state solution. And I'll come back to why we're looking for a steady state solution in just a little bit. But you have two sources. You have the particle sinks at the boundaries, and you have the particle sources due to the ionization collisions and the secondary emission. You have current hitting the cathode, which is going to impact the voltage. So without an external circuit model, you really wouldn't be handling the physics correctly, because in a real setup, you would have to sort of deal with Ohm's law somehow, and the simplest way to deal with Ohm's law is just by including a resistance. And then furthermore, you can imagine that near the cathode, you're going to be getting a large buildup of secondary electrons, and you're going to have some sort of pressure balance type between these thermal secondary electrons wanting to expand out and trapping due to the magnetic field. So the problem, you can write down all of these conditions, but then coming up with a way to balance all of this probably isn't possible analytically, except under the simplest conditions. Okay, so VSim can help with that. It's easy to change parameters, run a simulation, and see how that impacts the outcome. Okay, so at this point, what I want to do is show you how to open the example. So I'll go through that, and then I'll walk through this example in some detail, showing you the different parts of this problem. So in VSim 12, you will you'll install the software, and then you'll navigate to wherever you installed it. And you'll just, if it's Windows, you'll just simply click on VSim Composer. And some of you have done this 100 times, so I'm preaching to the choir. But if you haven't, then this is, it's as simple as this. You open the software, you go to File, New, from Example, expand this VSim for plasma discharges. And you'll see all of our plasma discharge examples here. You'll expand sputtering, and then you'll click on this cylindrical magnetron sputtering. You will probably want to create your own directory, call it whatever you want. I already have this saved, but, and then you just save it in all of your, the input file along with all associated files will be saved in that directory. Okay, so now one thing that we don't show a lot of people, but we're certainly not hiding, is you can scroll this out here and see what are the associated files. The associated files are our cross-section tables. So these are needed for the collisions. So we have a cross-section table between argon and electrons. And then we have some excitation cross-section tables. And then there's an ionization cross-section table. I typically use LXCAT to get my cross-section tables, but if you need help with that, I'm more than happy to help you find your cross-section tables for your problem. We also have this external magnetic field, which we are supplying for this problem. Okay, so it's opened once we see in the upper right, simulation setup is ready. I'm going to minimize this, and I already have the simulation that I've run. Some data generated that we can look at. But before we get to that, I just want to walk you through in more detail this setup. Dan already went through a very high level, so everything I'm going to do here is particular to this problem. The first thing that we've already added the necessary parts and the basic settings to include particles and reactions. But if we expand this particle dynamics tab, then these are all of the kinetic species included in this simulation. So we start with a seed population of electrons. This is just to get the simulation going. These electrons will quickly be absorbed at the boundaries and also create secondary electrons at the cathode. And then the secondary electron is what gets produced through collisions and through secondary emission. Argon ions are also part of the seed population, but I didn't create a, quote, secondary argon ion population. So all new argon ions go into this population here. And the sputtered material is the neutral cathode, or sorry, the neutral copper at the cathode. So you can see that the electrons are seeded using these particle loaders here. Particle loader option right here. And in order to seed that population, we have to give it this velocity distribution, which you can do by right-clicking and then finding this space-time function called Maxwellian electron. Okay, so you're going to want to go through this example in much more detail than my quick overview here. So hopefully this gives you a good starting point. I want to also focus on these boundary conditions. In particular, I want to focus on the electron absence-safe cathode boundary condition. What will happen is that now, actually, I think I can, let me just point out one thing real quick. All the plots I'm going to show you have R on the horizontal and Z on the vertical. In this visualization window, those are flipped. So the cathode actually sits right here. All right, so this cathode right here, the electrons are going to impact it and create secondary electrons. And they're also going to be absorbed. And absence saved means that particle data is recorded when it hits the boundary. And I can use that information somewhere else in the simulation. So I'll show you how that's used in just a minute. So I have an equivalent boundary condition for all my particles. So for the secondary electrons, I have a secondary electron, absence saved cathode, and the same for the ions. Now what I can do is, so once you've created the particles, and those particles are going to, during the simulation, be hitting the cathode, and it's going to be creating a current onto the cathode. It's that current that gets fed into the external circuit model. So, so let's just store that in the back of our head that we have that boundary condition, which I can now use somewhere else in the model if I need to. Finally, I have my neutral fluid, which I just called neutral argon. And that is used in the reactions. So let's go up here. And there's a new feature in VSim 12. It's this, this option right here called external circuits. To create an external circuit, all I have to do is right click on here and click on add resistive voltage source. And once I do that, it creates this new external circuit, which you can rename to be whatever you want by double clicking. Once I have the external voltage source, I right click again, and I need to add my boundary conditions, which contribute to the current, so whatever boundary I'm interested in. And to add that boundary condition, I have to use an absence saved. So if I right click, I go to particle boundary condition, and I have a boundary absence save, I've got a cut cell absence save, I've got an interior absence save. Any of these absence saves can go into the external circuit model with one caveat. And right now, we don't have the cut cell absence save that can be used in the external circuit model. So we started off by adding this capability at the boundaries. So right now, I've used the boundary absence save and the interior absence save, both of them, to collect particles at the cathode. So when I right click here, and then I add a new current source, now I'm going to go down here. So I added current source 0, and I go down here, and I double click, and these are all the boundaries that I can include. So I wanted to do secondary electron. I wanted to do all the cathode. Okay, so that's where electrons, absence save, and then the next current source is secondary electrons, absence save, cathode, and the third current source is argon, absence save, cathode. So that's how you add an external circuit to your simulation. Alrighty, and then the last thing that I'll discuss, well, okay, so now we need to know how to include that as a boundary condition. Because the external circuit is now a special type of a Dirichlet boundary condition. And Dirichlet just means that you're specifying the voltage. The Neumann boundary condition is where you specify the electric field at the boundary. So all of my boundary conditions are Dirichlet. I've specified the voltage at every boundary in the simulation. And you can, so if I were to right click and add a new boundary condition, a new Dirichlet boundary condition, then you would have all of these options to choose which boundary, and then you would right-click, and then now one of the options to add is the external voltage option. So it's a new option available in VSim 12, and so that's external voltage 0 here. Okay, so that, and so if we actually look at the external voltage, then these are the parameters that you need to specify. You need to specify your initial starting voltage. So in this case, it was negative 470 volts. You need to specify some resistance, which is, 5,000 ohms. And then the time constant is essentially a low pass filter because you're going to be getting a lot of electrons hitting the cathode, you know, on the time scale of the ratio of the thermal velocities compared with the ions. So you kind of want to average over the electron contribution so that it's not so noisy. So in this example, I'm averaging over 5,000 time steps. Okay, so the and then the last thing I'll go over in the basic settings is just the reactions that we've included. So once you've added the reactions in the basic settings, then you have all these options here to add. I'm only looking at the particle fluid collision. So the fluid is the argon neutral gas. And then if you want to add a new collision, you can right click and you can add any of these types of collisions. So I've included elastic collisions between electrons and neutral, and then I include ionization collisions and a couple of different excitation collisions. So feel free to add many more that surely will contribute to this problem. So this problem is just to demonstrate how to set up a magnetron sputtering type problem, and you know, you, the user, are expected and it's hoped that you would then add in whatever physics you need to get your problem working. The example helps you fast track your setup. Okay, so now it won't let me do anything unless I save it. And I didn't actually change anything, but I double clicked on some things and it thinks I changed it. So let me answer a couple of questions here. Does SEC electrons include electrons from bulk ionization or only electrons from the boundaries? So the secondary electrons was both. So when a electron or ion hits the cathode, there's some chance that a secondary electron will be emitted in that process. We provide the secondary electron yield function, which basically gives you the probability as a function of energy, and that secondary electron is emitted into the SEC-elect population. Likewise, any ionization collisions will also go into SEC electrons. Is it possible to include an emitter? Yep, you can emit from any of the boundaries that you think need to be emitted. So that the which of course that will impact current, which will impact the circuit, but yeah, you can put in an emitter. Okay, so once the simulation's done, which I ran for 120,000 time steps, once you've finished setting up the simulation, you just go to run, and it's all set up just to hit the run tab and get going. I've already done that for this problem, so I'm not going to do that here. This is a pretty computationally intensive problem, so the more cores you can throw at this, better, with being limited, of course, by MPI decomposition. Probably 32 cores would be a good if you wanted to do it in a few hours. I ran this also on 8 cores, and it probably took about 8 hours, 8 to 10 hours to run on 8 cores. On 16 cores, you know, about half that. So, and then once you've finished the simulation, then you can go to analyze. So I used a few analyzers in this problem. One of the analyzers I used was called add species with kinetic energy. It's the first one at the top. What this does is this computes the energy of the particle in the EV, and it actually creates a new data file. So typically when data is saved, the data that's saved, the particle data that's saved is position. So in this case, V and R, and then the velocity, Vz, Vr, and Vphi. The last quantity saved is weight, and this creates a 7th category, and that is the energy. Once I have run that, which I can just run, actually I might, everything's pre-populated, so you can just hit analyze. Then you come over here to compute the Debye length, and I've had to, let me actually check. Okay, so this should work. So let me just run this. Over here, we only want to output the magnitude of the energy. Okay, so I already have the data, but it's just overriding it. So once you've run that, then you're going to want to run this analyzer. In the population, I'm running this analyzer on the secondary electrons, but it's this new data file called secelec with kinetic energy. So if you went into your directory, you would find that data file. Now this analyzer is very, very handy because it's very important to make sure that you're resolving the Debye length. So if your cell size is larger than the Debye length, then you'll get numerical heating and you'll get grid instabilities. And the simulation may not crash, but you're probably going to get the wrong answer. It may crash for other reasons, because once you're no longer resolving the Debye length and you get grid heating, then the particles will unphysically heat and they can zip right through your ghost cell and you'll get a segmentation fault. So that's very, very frustrating. So I encourage you to ensure that you're resolving the Debye length. So one of the outputs of this is the ratio of your, let me write this down actually. It's I always forget if it's delta X over lambda or lambda over delta X. So you want delta X, sorry, so we're outputting lambda over delta X. So you want that to be greater than 1. And I've more than satisfied it. So right now my largest cell size is, is lambda, the Debye length divided by 7. So about. So I'm more than resolving the Debye length. You can get this very close to 1 and everything works just fine. But the minute this dips below 1, you could start running into problems. Okay, and then this also generates the electron temperature and the secondary electron density. So some good diagnostics it creates. And then lastly, I use compute particle number density. And I actually use this to create the copper density because I was curious what copper densities I was creating. Okay, so once you've run these analyzers, then you can click on Visualize. And I'll go ahead and reload the data just to show you what that looks like. Now, let me just give you a heads up. If you load the data and then you say, oh, I want to run an analyzer, that's fine. You go back, you find the analyzer you want to run, and you run it, and that's going to create a new data set. Then when you go back to visualize, you'll need to reload that data set into Composer. It won't just automatically show up. So you have to reload the data. Now this shows the, I purposely plotted the data like this to show you how to swap axes. So this is a plot of the potential. Actually, let me first actually show you the diagnostic I've been using to determine whether or not I'm in steady state. So I'll have to skip that step. But I don't have to skip that step because I plotted it in the documentation. So I didn't download the data, it looks like, onto this computer. So let me take this as an opportunity to show you how to access our documentation. So one way is through these PDF files, and another way is online. So choose whatever you're most comfortable with. So I'm going to open up the reference manual. Oops. Sorry, I'm going to open up the examples documentation. And then just like finding the example itself in VSim, you will go to VSim for plasma discharges. You'll go to sputtering, and then you'll click on this cylindrical magnetron sputtering, and you get my explanation of this problem. And I went into some detail on this because this example showcases many of our capabilities. So I have how to set up the magnetic field section, how the plasma is initialized section, boundary conditions. So all of that is spelled out in this example. So if I go down to some of the plots that I created for this example, which I'll show you them how to visualize them in VSim in just a minute, one of these plots is a history plot. And this is how I determined that we had reached steady state. So it's important in your setup for this to be a goal. And the reason is because in any kinetic model, maybe you'll run out to tens of microseconds, or maybe 100 microseconds, which could take a day to model. But your actual setup might go out to milliseconds or even seconds. If you've reached steady state, then you know that you could extrapolate your data out to millisecond or second timescales. Nothing's going to change. That's the definition of steady state. So this is a plot of the cathode voltage. You can see that we started at negative 470 volts, and it did a little bit of adjusting. And it settled down to this value that was close to our initial value, but not too far away, so that it was able to find that steady state solution. The bottom plot here is a plot of our secondary electrons. And again, after about, this is milliseconds on all right, cut that off. I'll fix that in the documentation. But this scale here is microseconds on the horizontal scale. And so we went out to about 1.4 microseconds. And after about 0.6 microseconds, you can see that the secondary electron population is pretty constant. And after about 1 microsecond, you can see that the cathode voltage is about constant. So this was our diagnostic tool. This history was our diagnostic tool for demonstrating that we had reached steady state. Now, if we wanted to plot, this is the voltage, then if you just open up a data overview plot, expand the scalar data option, and then click on Phi. We can swap the axes. If you're more comfortable with the radial direction being horizontal, which for these types of problems they typically are, then we just swap them, and nicely we have a coordinate system that is maybe more easy to work with. We can superimpose data, particle data on top of this color contour field data plot, and you can choose any population you want. We'll just choose this secondary electron population, and you can change the size here of your dots, and you can see them growing with time. Okay. If you're going to superimpose data like this, the field data needs to be plotted first, and then you can plot the particle data on top of that. This was a plot of our magnetic field. And again, you can swap the axes nicely here. And again, the particle data can be superimposed. And finally, the thing of interest is for the industrial applications is the formation of the copper. We could plot the copper as particle data, but I've chosen to compute the density and plot the density of this. This is the density of the sputtered copper. Now, copper is not going to move very far on microsecond timescales. So you could actually load this data into a second simulation and just do sort of particle trajectories over millisecond timescales to see where these particles land. So you might have a modeling effort that's two parts. One is to compute the actual sputtered copper on the surface, and then a second simulation would be to see where they land in your chamber. Because after all, you want to use this copper to coat something. You can change the color scale if you wanted. If you wanted maybe to, get a more sensitive color scale. So you can play around with the color scale. And again, you can plot I'm going to plot argon ions on top. Yeah. I know. I changed my limit. I'm not looking at the whole. No, let me swap like I've done with the other. There we go. All righty. So this is just the argon population on top. You can see where they're mainly impacting the cathode. So, that could be a useful diagnostic. And then, I just want to reiterate that this sputtering process is a kinetic process. So, and by kinetic, what I mean is that the angle and the energy that they impact the surface, and you can only get that in a kinetic code. You can't, you can get in a fluid code, you can get the bulk fluid velocity, but you're not going to get the phase space information about how an individual argon ion hits the surface, because that's averaged out in the fluid code. You've integrated that information out. So if you, and to get the sputtering right, you need that that phase space information of each ion impacting cathode to get the sputtered yield correct. Okay, so I think that's the main things I wanted to show you for the magnetron sputtering. And so, the parameters which, you may want to start fiddling with for your particular setup could be things like external magnetic field. If you wanted to change the magnetic field, you need to supply your own magnetic field. We can read in a magnetic field from some other source you may have. You'd have to save the data as a text file, and then we could read it in. You might want to fiddle with the neutral pressure. You might want to fiddle with your cathode voltage. Those are just 3 parameters that greatly impact the evolution of magnetron sputtering. All right, so to summarize, magnetron sputtering is a common industrial application of thin film deposition. It's used in metallization and integrated circuits. It's used for coating. It's used in photovoltaic solar cells. You can use VSim to fast track your industry application. Something that might take weeks to fiddle with and get a new configuration, you can model in a few hours in VSim. So in those few weeks, you could run through dozens of simulations to optimize your setup. I think I've hit the kinetic approach enough, but it's vital for this problem. So, alrighty, that's all I have to say about this particular problem. We could go on we could have a whole conference on magnetron sputtering. So we've just scratched the surface here, but hopefully this gives you a good starting point.
Thank you, Daniel, for that presentation. I know we have a couple of questions that we can answer here. So this example is going to be, or it is in VSim 12, our release that is coming out this week. So you will be able to try it for yourself. I know that this is also a bit of a more challenging problem, right? Daniel, you said this is one of the kind of trickier ones that you've done. So we are definitely encouraging our users want to make sure that they know that this is going to be something you may want one of us or one of the application engineers to work with you on. It's a very popular application, and I know there's a lot of demand, but we want to make sure that it's right. And so that's part of what you get. You do get support hours with every software purchase. And in a case like magnetron sputtering, we actually can set you up where you can purchase additional consulting hours to make sure that you have the right support for your problem. So let's go on to our questions. It looks like the first question says, does secondary SEC electrons include electrons from bulk ionization or only electrons from boundaries?
Yeah. So yeah, I answered these while I was waiting, but I'll go through them
I'm
again.
so sorry. Okay.
No, it's okay. Just to reiterate, in case someone was not listening, it's both. So I populated the SEC-elect population with both ionization and the secondary emission off the boundary. Yep. But I'd like to just point out the flexibility in VSim. You could create your own. You could have a population of both if you wanted. If you wanted to keep track of both separately. I know yesterday that Andy had mentioned tagged particles, which is a very neat capability in VSim. But that's, as far as I know, that's only available in a more sophisticated expert type setup. So one workaround of tagged particles is just to create separate populations. So you could create a SEC-elect population, and you could create a SEC or an ionization electron population, and keep track of them separately.
Okay. If there's any additional questions, you can type them in the Q&A box at the bottom. We've got just probably 1 or 2 more minutes before we have to get set up for David Smith for our final talk. So just see if we have anything else. And this presentation, just a reminder, so all of our presentations will be on the TechX website and the TechX YouTube page. This will probably be the first one that we get up. And we will get the slides from this presentation up there as well. So you will have access to these along with the documentation that Daniel showed to assist you as you work through the problem. So I don't see any additional questions, Daniel. So I think you are done for this TWSS.
All righty,
Thank you so
you. Welcome.
All right, coming up, we have one last presentation from David Smith in about 7 minutes. We'll see you then.